Hi everybody, and welcome to our unit on thermochemistry. All right, when we're talking about thermochemistry, we're talking about studying the energy changes that occur either during chemical reactions or changes of state or even changes of temperature. Okay, there's something known as chemical potential energy, and how we get energy from reactions is that there's actually energy stored within those chemical bonds, and energy is transferred when bonds are broken and bonds are formed. Okay, another abbreviation having to do with energy that you need to know is heat. All right, energy that transfers from one object to another is known as heat, and it gets the abbreviation of a lowercase q. Okay. Two major units for measuring heat, okay, heat flow, and one of these should sound very familiar to you. One is the calorie, all right? A calorie is the amount of heat needed to raise the temperature of 1 gram of pure water 1 degree Celsius. All right. Calories should sound familiar to us because our food energy is given to us in calories. But just to let you know, kind of an interesting fact about the United States, if you look at any of our food packaging, you're going to actually notice that that C is an uppercase C. That is because it is not a true, all right, scientific calorie. Instead, it is a kilocalorie. But because we are not super familiar with the metric system, the food packaging people decided to use a capital C for kilocalorie in this country. If you look at food packaging from other countries, they will actually have it as kcals for kilocalorie. The SI unit for energy that we're going to be using, all right, is what is known as the joule, okay? And that is a capital J for joule. 1 calorie is equal to 4.184 joules. And this is going to be a number that we're going to be using quite often, all right, because it is actually what is known as the specific heat capacity of water. Okay, so specific heat capacity is the amount of heat needed to raise the temperature, again, of 1 gram of a substance 1 degree Celsius. All right, for water, the specific heat capacity, so we would write it as Cp of water, and realize this is of liquid water. Ice and steam will have different specific heat capacities, but today we're just going to be talking about liquid water. And the specific heat is written as 4.184, and that's joules over grams times degree Celsius. All right, that is the specific heat capacity for liquid water. We're going to be using this number all of the time. In your notes, I've given you this little table that gives you the specific heat capacities of some other substances, both in terms of calories and in terms of joules. Water is one you really should know without having to look up. The others are all numbers that you would look up. All right, so how are we going to use this specific heat capacity? Well, we're going to use it using this equation, and this is a rather famous equation. It's used in chemistry. It's also used in physics quite a bit. All right, and some people call it the MCAT equation, and you're going to see why. Okay, so the amount of heat or energy, kind of a confusing thing in thermochem is that we tend to use different words to always mean the same thing. So heat, energy, it's fine. We can use those interchangeably. So our energy is going to equal the mass of the substance we're dealing with times the specific heat times the change in temperature. So you can kind of see where you get MCAT from that a little bit if you want to. CP stands for specific heat. That is the specific heat capacity. Delta T, okay, you'll notice in the notes I have a hard time putting in triangles, so you're gonna have to fill those in. So delta means change in, so delta T is the change in temp. And M is gonna be our mass, and that mass should be in terms of grams because our specific heat capacity will be in terms of grams. Okay, so let's go on ahead and do some practice with this. If you feel comfortable with these, or if you've done them already in another class, feel free to pause the video and you can do them on your own, or you can just watch along with me. All right, I'm just going to go ahead and write the equation again up here because I know I'm going to be using it. All right, so mass times the specific heat times the change in temp. How much energy is given off when 25 grams of water is cooled from 99 to 36 degrees? So here we go. I'm looking for Q. I'm looking for how much energy. My mass is 25 grams. My specific heat is 4.18. You can kind of lose that 4 at the end if you want to, just to make the work a little bit faster. So you'll notice that I do that on answer keys and things. All right. And then the change in temp. Okay, always make sure your change in temp is a positive number. So it's going to be 99 minus 36 degrees Celsius, all right, which is 63 degrees Celsius. You're now just going to multiply these three. Note that the units do cancel out because grams will divide out there, degrees Celsius will divide out. We'll be left with joules. We're looking for energy. That is a good thing. All right, and when we punch that into our calculators, you're going to have 25 times 4.18 times 63, and you get about 6,584 joules. Okay. All right. Don't be surprised when you're getting a large number for joules. A joule is a really small amount of energy. Oftentimes we're going to talk about it in terms of kilojoules. So don't be surprised when that happens. Okay, let's take a look at our next example. All right, number 2. When 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees, the temperature increases to 85. What is the specific heat of olive oil? All right, so this time, okay, we're not going to be looking for energy. I've already given that to you. This time we're going to be looking for specific heat. All right, so my energy is 435 joules. My mass is 3.4 grams. I'm looking for specific heat, so I'm just going to leave that there as my variable. My change in temp is it went from 21 to 85, so 85 minus 21. Remember, we want to keep that delta T a positive number. Think of that as you're going through. All right. All right, we're going to do the math for this, and when you do, you are going to come up with that your specific heat is about 2.0 joules per gram times degree Celsius. All right, we're going to be doing a lot of practice with these, so if the algebra is a little shaky, don't worry, we will work that through. It will all work out nicely. All right, our last 2 practice problems for today is going to talk about what happens when you mix 2 things. And think of this really, really simply. If you have hot water and you put it with cold water, all right, and you put them together, you're going to end up with warm water, right? So you're going to end up with water that has a temperature in between the hot and the cold. Same thing is going on with these problems. We're just doing them mathematically. All right, so we say that these are, what you want to think about is heat gained is equal to the heat lost. So what that means is you're going to be setting up 2 specific heat problems and you're going to be setting them equal to each other. All right, so let's go through, and it doesn't matter whether you want heat gained first or heat lost first, that doesn't make any difference. But let's take a look at our work. So 150 grams of water at 75 is mixed with 200 grams of water at 30. What is the final temperature of the system? Okay, so let's first deal with this 150 grams. All right, so my 150 grams of water, all right, and remember, water has a specific heat of 4.18. Okay, and that 150 is starting at 75 degrees Celsius. Okay, starting at 75. I'm putting it with something that's at 30. So the final temperature is going to be lower than 75. So I'm going to say, because this is supposed to be my delta T here, this is my change in temp. It's starting at 75. I don't know where it's going to end. That's what I'm solving for, okay? But I know it's going to be lower than 75. So I'm going to set it up as 75 minus X, because remember, I want that delta T to be a positive number. So this 150 grams is actually going to be losing heat. So this is my heat lost. Well, if that heat is lost, it has to go somewhere, and it's going to go to the water that is gaining it. So heat gained. Let's talk about that water. This is the 200 grams of water. So I have 200 grams of water. All right, again, the specific heat is 4.18. All right, joules per grams times degrees Celsius. But now for the delta T for this one, we want to be careful. This 200 grams started at 30. The final temperature is going to be higher than 30. So in this case, we want to do X minus 30, all right? Because again, we know it's gonna be higher and we wanna keep these a positive number. It's gonna really work out much nicer that way. All right, so before we continue on with the math, there is a shortcut that you can take. If you notice, you're dealing with liquid water in both cases, so you can just automatically divide out that 4.18, okay? Because it's water, you don't, and it has the same specific heat, you don't have to deal with that. Okay, so now let's look at the algebra problem. You have 150, okay, grams times 75 minus x is equal to 200, and this is still grams, and this is degrees Celsius, but we're not going to worry too much about that, x minus 30. Okay, so now it's time just to do a little bit of algebra with this. All right, and I'll walk you through the steps of this algebra. All right, so 150 times 75, right? We're just distributing 150 times 75. Feel free to do this faster, that's totally fine. But for those of you that need a little reminder, so that gives me 11,250. Now I'm gonna go 150 times x, so that's minus 150x is gonna be equal to 200x, because I'm distributing that 200x minus, and then 200 times 30, and that's gonna give me 6,000, all right? I wanna get my x's on one side, I wanna get just my numbers on one side, all right? So what I'm gonna do is I'm gonna add 6,000 to each side, right? So plus 6,000 plus 6,000 here, all right? So, and I'm gonna add 150x to each side. So plus 150x, plus 150x. All right, so what that's gonna end up giving me, okay, is I'm gonna do 11,250 plus 6,000, gives me 17,250 is gonna be equal to 150 plus 200, 350x. You're gonna divide each side by 350. All right, so 17,250 divided by 350. And that's gonna give me an x of about 49.3. And now we wanna ask ourselves, does that make sense? We did a lot of math there, but we wanna make sure our answer makes sense. We had water that was at 75, we added it to water that was at 30. All right, is 49.3 degrees Celsius between those two numbers? Absolutely. So this is our final answer. It's always really nice when you have problems that you can kind of check with logic as well. All right, let's take a look at this next one. 25 grams of an unknown metal at 150 degrees is added to 50 grams of water at 25 degrees Celsius. The final temperature of the system is 39 degrees Celsius. What is the specific heat capacity for the metal? So again, let's set it up. We'll start with this unknown metal because I have it written first. That's going to be our heat lost because it's going to get colder. It's going to be equal to our heat gained. All right, so we have 25 grams of that metal. Okay, the specific heat of it, we don't know, so we're just gonna leave that as specific heat. It starts at 150 degrees Celsius. It's added to water. The final temperature of the system is 39, so we're gonna go 150 minus 39 degrees Celsius. Okay, well, where did that energy go? The energy went to the 50 grams of water. So you have 50 grams of water. You know the specific heat of water is 4.18. Okay. And water went from 25 to 39. We want to keep that a positive number. So 39 minus 25 degrees Celsius. All right. So now it's just time to do a little bit of math with this. And again, just because these are shorter notes, I will go on ahead and help you with this. So 150 minus 39, I'm going to do this one first. This gives me 111 degrees Celsius as my delta T times 25. So, and I'm just going to turn that CP into X. So this gives me 2775X is equal to, we're going to move over to this side, 39 minus 25. That delta T is 14 degrees. Going to multiply that by 4.18. All right, and multiply that by 50. And that gives me, I'm just going to write it over here, 2926. You're going to divide each side by 2775. All right, and then X is going to give us, so I have 2 divided by 2775. about 1.05, 1.05, and this is specific heat, so it's joules times over grams times degrees Celsius. And that is your final answer. All right, you'll note with all of these, we are keeping everything in degrees Celsius. We're not dealing with gas laws anymore. So keeping all of these in degrees Celsius is just fine. Okay, you're gonna get some practice with this. Have a great day.